So in the last lecture, we were looking at radiation properties, and we looked at ways of calculating radiation parameters. So today, what I'll do is I'll start with the application of whatever we've learned so far, and this is regarding calculation of radiation exchange between two or more surfaces. So two is quite easy, but we will do a general scenario where we have more than two surfaces, or let's say n number of surfaces in a problem, and they are exchanging radiation. But I will make an assumption throughout, and the assumption that I will make is that these surfaces will be separated by a non-participating medium. So as usual, I will not consider the case of a medium that can absorb or even emit radiation. So that I'm going to take off straight away. So to do these kinds of calculations, or to do these kinds of design exercises, we typically start with a new parameter, which is what is called as a view factor. And the view factor sometimes is also called as a shape factor. It is called as a shape factor, or sometimes you will see some books, I think, even call it as a configuration factor. But it is based on our whatever we did in the last lecture, which is about how one surface sees the other surface. So the problem is actually quite simple in this case. Let's say you have two surfaces, okay, two arbitrary surfaces. Let's say one is here. This is surface A1, and or rather, let's say AI, to keep it general, because we'll have n number of surfaces. And let's say its temperature is Ti. I can draw the normal vector for this surface, which is, let's say, Ni vector. And somewhere I also have another surface with which this surface I can actually exchange radiation. So let's say there is another surface AJ with temperature Tj, where whose normal vector is maybe something like that. And say I take an elemental area on each of these surfaces. So let's say we take an area DAI and an area maybe DAJ on each of these surfaces. And if I draw the line connecting these surfaces, these elemental surfaces, let's say this distance is r, and the normal vectors make an angle, polar angle theta I and theta j with this line. So that is a setup that we have two surfaces. We want to look at what is the view factor, or what is actually even meant by the view factor first. So you should just remember that I've taken these elemental areas. So please remember that r, theta I and theta j are actually variables. They will depend on the elemental areas, or the position of these elemental areas on these overall surfaces AI, or surface I and surface J. So they will not be constants throughout. If they were very small surfaces, of course, if I can say AI and AJ were very small, minuscule, then we can assume them to be constant. But not in the analysis that we are developing. We will look at more general analysis. So the view factor that I'm going to write is going to be a number Fij with subscript, so F with subscripts I and J, and this will basically define the fraction of radiation that leaves surface I and that is intercepted by surface J. So if I is radiating, or is emitting in all possible directions, I am asking you now that what is the amount. Fij denotes out of the entire amount of radiation leaving surface I, how much is intercepted by surface J, okay, or how much is captured by surface J. So the idea of doing this is to somehow be able to write, if Q is the amount of radiant energy going from, let's say, I to J, then I want to write Qij as AI times the radiosity of leaving surface I times Fij. So Aiji is the total radiant energy leaving surface I, but Fij then tells me that out of the total radiant energy, how much is reaching surface J. Okay, so I've defined this like, so please notice I've said Q I to J. There's an arrow basically. It's saying from I, how much is going to J. So I want to write this expression in this form, and for that I need to somehow calculate what should be Fij. If I have Fij, I can straight away calculate what is the amount of radiant energy reaching surface J. So we can start with, since we defined elemental areas, we can start with the differential analysis. We can say, let's say, dq, which is a amount of energy leaving elemental area dai and reaching daj, would be intensity at surface I times dai cosine theta I, very similar to what we defined in for the intensity or the radiant intensity, the definition of intensity, times d omega. Now d omega should be of surface J as seen from I. That is a solid angle. Okay, so solid angle subtended by surface daj as seen from dai. So we can take it a little further. Now I can also write this as I dai cosine theta I, d omega ji will be just daj. Basically, that is now the projection of daj along this line, along this line. Okay, so projection of that along this line. So daj cosine theta j by r square was the definition, the way we defined solid angle earlier. Okay, now we'll make an assumption here, and this assumption would be required to keep the analysis simple, and so that we can do at least some estimation. So the assumption that I'll make, the second assumption that I'll make here is, apart from the fact that medium is non-participating, is that this surface I actually emits and reflects diffusively. So we'll assume surface I emits and reflects diffusively. What it means is the directional dependence of the radiation is being taken out. So it is the same intensity in all directions. It basically means that I could be written in terms of radiosity of surface I as Ji by pi, and which we did earlier. So once we have this, we can now write dq I to j as Ji cosine theta I cosine theta j dai daj by pi r square. And so this is the amount of radiant energy going from surface dai to daj. If I have to calculate the total amount, the total radiant energy going from surface I to surface j, I should integrate this expression over both areas, over both ai and aj. So we can write qij to be the integral of ji cosine theta I cosine theta j dai daj by pi r square, and of course integrated over surface ai and aj. And now I'll make one more assumption, which is not very critical, but something which will help. I will assume the ji is uniform over surface I. That, so basically I'm going to assume that the surface I has a uniform radiosity. So this is another assumption that I'm going to make. By making this assumption, what I'm doing is I'm making ji independent of the integral over dai. So I can pull it out, and then I can write qij by aiji, which would be 1 by ai integral over ai aj cosine theta I cosine theta j pi r square dai daj, to be, since if you remember I said earlier I was mentioning that we want to write qij as aiji into fij, so this should then be equal to fij. So the view factor would be this integral, which we need to compute to be able to calculate the amount of radiant energy leaving from surface I and reaching surface J. Okay. So notice the form in which I'm using the subscripts, even though I didn't mention it very explicitly. But what I'm saying is the first subscript is the originating surface, the second subscript is the surface or the destination. Okay, so source and sort of, if you want to call it the sink, but source and the destination is what I'm trying to define by the using the subscripts in this form. Now, there are few things that, or you have to remember when we derive this based on a few assumptions. The first assumption was that the surface I, or rather, I would now generalize to all surfaces. I'm not saying this for surface I, but the way we are going to solve these kinds of problems is that we will assume all surfaces involved are diffuse emitters and diffuse reflectors. So even surface J and any surface, I mean, let's say there are n surfaces. So surfaces 1 to n are all diffuse emitters and diffuse reflectors. That will be assumed so that we can calculate Fij. And the second assumption will be that on each of these surfaces, the radiosity is uniform. So we will keep making these, we'll use these assumptions throughout. Now, the advantage of making these assumptions is that if I now look at this integral, if I forget about AI, if I just look at this integral alone, okay, this if I just look at this integral, it is clear. I hope it's clear to you that if I was to compute the amount of radiant energy leaving surface J and reaching surface I will have the same integral there, except the integral will actually have a 1 by aj here in the front, right? So the integral will be the same. So whether you do it from I to j or j to I, the integral is the same, which basically means that ai fij would be the same as aj fji if I just multiply ai on one side and aj on the other side. This is what is called as a reciprocity relation. And this is also a powerful tool in most of these radiation based calculations. So the idea is that if I know the view factor from surface I to j, knowing the areas of the two surfaces, I can also calculate the view factor from surface j to I. That is just a simple way of saying this. So how do we apply this, or how do we even first of all solve these kinds of problems? So the idea comes down to calculation of view factors in most problems that we will do now. So as an example, let me take an n surface problem. Let's say we have n surfaces in an enclosure. So say we have an enclosure which is made of n surfaces. Say something like that. We have an enclosure which has these walls, and each of these walls is a surface. I mean, each of these. So say we have surface 1 which has temperature T1, surface 2, temperature T2, T3, so on till we have, let's say, Ti, and maybe the last one is Tn. So we can count these surfaces based on the vertices. And so each surface also has its own radiosity. So maybe surface I, as I said, it has uniform radiosity, so it will have some radiosity of this type. That is the assumption that we made. And each surface will have its, of course, its own radiosity. Now, what I'm saying is with the view factor is there is a very powerful uh, way of using this. You need to understand that if I look at view factor Fij and sum it over all j going from 1 to n in this n enclosure problem, then this sum should be equal to 1. That is just conservation of energy, if you want to say it. Because what it's saying is that radiation leaving surface I in an enclosure must be intercepted by someone. It cannot just disappear. So it is being, so that is basically accounting of all radiation. So all radiation leaving I reaches surface, some surface j. By the way, the summation can also include surface I, because if surface I has a concave shape, hmm, then it can actually, and I'll show you some examples today, that then it can actually intercept its own radiation. So this can include the summation from j1 to n can actually include surface I as well. The only way it cannot include surface itself, rather, is if the surface is maybe plane, in which case Fii is 0, or if it's convex, in which case again Fii is will be 0. In both cases, because radiation leaving one side will not reach the other side. And I mean, the way I typically think of it in these problems is, and I'll show you the trick actually. If you have a surface, let's say, right, and the way to say whether a surface will obtain will capture its own radiation or not is that if you take a point on the surface, okay, there's a point here on the surface, and I join it with some other point on the surface, let's say this point. If I join these 2 points, if they do not happen to be on the, on the in the on the side where radiation exchange is taking place, so if this is a side on which radiation is supposed to go out, if that line is not on that side, that basically means that Fii will be 0. That point, these 2 points don't see each other, so Fii will be 0. And that is the reason we are saying that for a plane as well, we are saying that it is just glancing. It is one of those limiting cases that the radiation just glances over, it does not even hit that point. So it's a limiting case. So summation Fij will be 1. Now, if I have an n enclosure problem, I will have how many number of view factors? This is important. If I have a problem of this kind, I hope you see that for an n enclosure problem, or an n, rather, n surface enclosure, not n enclosure, n surface enclosure, we will have n square number of view factors. So think of it this way, that if you will have for each surface, you will have these Fij's. So j will go from 1 to n, and I will also go from 1 to n. So you have n square number of view factors. If I have to calculate these n square view factors, I will need n square number of relationships. So what are these n square number of relationships? Okay, so what are the ways of calculating these n square view factors? So one way is to use these n linear equations and view factors. So n linear equations, and by linear equation I mean this equation. Let me highlight this equation. We will have n such equations, but we need more. The second thing that we can use in addition to these n linear equations will be the reciprocity relation. So the reciprocity relation will be actually a relationship between these Fij's, that they are not all independent. So we will have NC2 number of relationships between view factors, or rather from reciprocity relation. NC2 because out of n you choose any two and you can write a reciprocity relation between those two surfaces. So this is second, but that still will not complete or give me the complete number of n square equations. The third will be you'll have to write NC2 number of integrals to calculate view factors. So integrals will mean that the view factor integral, this integral. For NC2 number of surfaces, and these could be any NC2, you can actually write these integrals, independent integrals. So once you have these, now the number of equations will be n plus 2nc2, and this will be just n time or n plus n minus 1 by 2 into 2, and that basically comes out to be n square. So we can then have n square number of equations to solve for n square view factors. But be assured, or thankfully for you all, we will do simple problems, so you will not have to solve n square number of equations anytime in this course. Okay, we will look at easier ways of doing this, and we will look at simplified problems, or problems where many a times these view factors would have been already computed for us, and you can just pick them out from either a table or a figure or something. So how do we calculate view factors? Let me start with the simplest possible case. Okay, let me choose an example which is probably the simplest example in this method. So let's say we have a two surface enclosure, and the two surface enclosure could be something like, let's say you have one surface which could be a sphere or a cylinder or an infinitely long cylinder inside another sphere or cylinder. So let's say this is surface 1, its area is A1. This is surface 2, its area is A2. So we can say 1 and 2. So one surface is completely inside the other surface, and we need to calculate what would be the view factors for this problem. So we need to calculate F11, F12, F21, and F22. There are two surfaces, so there should be two square number of view factors. So that would be the number of view factors that we have to calculate. So clearly F11 will be 0 because surface 1 is convex, it doesn't see itself. And I hope you now understand what I mean by convex now, that this surface will always emit outwards, it will never receive its own radiation. So F11 will be 0. So that means from summation of all f's, F12 will be equal to 1, because F11 plus F12 is 1. So F12 will have to be 1. If F12 is 1, I can write A1 from the reciprocity relation, A1 F12 to be A2 F21, which means F21 will be just A1 by A2, since F12 is 1. And that means F22 will be 1 minus A1 by A2. Okay. So I hope this is clear. We solve this problem without actually having to calculate any integrals, because the problem could be solved by inspection, I should say. You don't need to calculate any integral. You can just solve this by looking at the geometry and saying what would happen. So that is a simple case. Let me choose a slightly more complicated scenario. Okay, let's say this is example 1. So let me choose example 2. This requires a little bit of thinking, but hopefully if you can see how I'm going to do this, you will be able to solve more difficult problems when you see them in the tutorial sheet. So say we have two surfaces, two inclined surfaces, flat surfaces of, let's say, length w, okay, with an angle alpha between them. Okay, and let me say this is surface 1 and this is surface 2, and I need to calculate what should be f12. Okay, both surfaces have equal length, and we need to calculate how much of radiation leaving surface I reaches surface, or rather how much of radiation leaving surface 1 reaches surface 2. So in itself the problem is not complete, because I can see, and I hope that you also um, agree with this, that all the radiation leaving surface I does not reach surface 2, or radiation surface leaving 1 does not reach surface 2. Some of it actually is lost in this area which we don't know anything about. So that is surroundings basically, right? Whatever. So you can think of it this way, that these two plates are here lying in the room, and there is nothing in the room, but these are just two plates lying there, and so of course some radiation will escape to the room. So what I can do is, and probably some might have figured it out, I can draw a frictional surface here which sort of closes this problem. Hmm. So I draw a surface 3 which sort of says that whatever radiation goes on this surface 3 is actually what is escaping into the room, or into the surroundings, if you want to say it. So let me say this is surface 3. So now the problem becomes slightly easier, because now I know that inside this enclosure radiation will be conserved. So the solution process is actually quite simple. Now this is only a case of geometry. Okay, so what I will do is I will drop a perpendicular from that vertex where subtends an angle alpha. I will drop a perpendicular, and by dropping that perpendicular, we then have this isosceles triangles, and so I can say that this length is 2w sine of alpha by 2. So that becomes a length, and of course it is has some depth inside which is very long. We can say it's unit. Let's say unit length. So the area becomes proportional to just the length in these cases. So now we can solve this. So we know that f11 would be the same as f22 would be the same as f33, which will be 0, because these are flat surfaces. So three view factors can be calculated just by inspection. Secondly, f12 plus f13 will be 1. So radiation leaving surface 1 would either go to 2 or will either go to 3. And similarly, f21 plus f23 will be 1. So radiation leaving surface 2 should either go to 1 or should go to 3. Now I will use, as I said, a lot of these problems have a lot of intuition to be used. So I can say that the triangles, the two, I mean rather the two lengths or surfaces 1 and 2 are of equal lengths. So clearly they are symmetric, or rather their view factors with surface 3 should actually be the same. So what I mean is, geometrically f13 should be the same as f23, and from 3 to 1 should be the same as from 3 to 2. That is just by geometry, that this is how it should be, if you look at from a just from this point of view of which way you're looking at. I mean, the lengths are the same, so we can use this judgment to say that, yeah, the view factors should actually be the same. Now the last one is quite good, because if f31 and f32 are equal and f33 is 0, this means these should be equal to half. So 0.5, f31 should be equal to f32, and that should be equal to 1 by 2. And then I can use reciprocity and say that a1 f13 would be a3 f31, and so a1 is just w times some length, I don't know, maybe unit length, into f13, and this should be a3, which should be 2w sine alpha by 2 into f31. So w gets cancelled, and so we get f31 to be f1, sorry, not f31, sorry, f13. We get f13 to be f31 is half, so we just get this as sine of alpha by 2, and that would also be equal to f23. And so uh, f12, sorry, f13 is over, so f12 should be 1 minus f13, and that is equal to 1 minus sine alpha by 2, which is what we actually had to determine in the first place. So calculation uh, from one surface to another typically, I mean, could require sometimes defining and or completing the enclosure, as I can say. So in this case, we completed the enclosure by adding a new surface, and then it became simpler to be able to calculate all these view factors. Now, these are simple examples that I've taken. In fact, for the tutorial sheet as well, I will. There are some very simple examples. Of course, you need to think a little bit about them, but they're simpler as compared to some more difficult scenarios. The difficult scenarios are actually listed in the book. They're given in the form of a table or in the form of a figure. I think if you look at Incrupera's in the book by Incrupera, there is, I think, figures rather 13.4 to 13.6, which lists down some of the more complex cases, and also tables 13.1 and 13.2, which have a list of some complex cases where the integrals have already been computed and you don't need to compute them. So we just need to see what the view factor there is. We can just plug in values and be able to, and we should be able to calculate what are the view factors for those scenarios or complex scenarios. Okay, so let's look at one more scenario where let's say we have radiation exchange between a surface I with a surface J, but surface J is composed of many more surfaces. So say we have a surface I, and it has an area AI, and it sees maybe a composite surface somewhere, okay, at some location. So the composite surface is made of many surfaces. So this surface J, which has a total area of AJ, it is made of components such as A1, maybe A2, and so forth, up to, let's say, small n. Yeah, let's not use capital N. So AK in general area. So AJ is clearly sum of AK, K going from 1 to N. So I want to now say that, or we want to derive a relationship, or rather, I want to show you what happens when a surface is composed of many sub-elements, and how do we look at, how do we calculate view factors in these cases? Because sometimes you will see, as I've shown you in the second example where I added a hypothetical surface, in some scenarios you will actually have to add hypothetical surfaces. I added one surface which is a flat surface, but you may see that sometimes adding additional surfaces can actually simplify calculations, and these surfaces actually have a very nice additive property. So we will use that additive property to be able to derive view factors in scenarios where maybe a direct equation may not exist. So if I look at this case, and if I look at, let's say, surface of view factor f going from surface I to surface J, where I'm writing the parenthesis to indicate that that surface is a composite surface, that it is made of many elements. Okay, that is this bracket is only meant to indicate that it's a composite surface. So I know that if I'm calculating how much radiation leaves I and reaches surface J, then it is the same as calculating how much radiation leaves surface I and reaches some surface K on this surface J. As I said, we can use this. It's just the additive property of view factors that we are going to use. Now, J, remember J is composed of many surfaces. So I will actually use something to turn this problem around. Let me multiply this equation here by AI. So if I multiply this by AI, I get AI Fij to be, and since I is an independent parameter or parameter independent of K, I can take it inside the summation and write this as AI Fik. K goes from 1 to N. And now AI Fik using reciprocity relationship can be written as K going from 1 to N AK Fki. So that basically becomes a multiplication of area of element K times the view factor of radiation leaving surface K and reaching surface I. And the left hand side itself here, AIFIJ, could be written as AJFJI. So what it means is that the view factor of a composite surface is a view factor of radiation leaving from a composite surface to some surface I could be written as view factor of individual elements from that surface divided by the total area of that composite element. So it's sort of like area averaged, if you want to say. The weights are areas in calculation of this view factor from a composite to one surface. So there are some examples that you will be doing which will actually use this idea as well. That if you're trying to calculate, let's say, view factor only of maybe one surface with this surface, you may actually add up additional view factors which can be easily computed, and using that you will see that we will be able to compute view factor from a single surface instead of, which may be harder to do otherwise. We may be able to do it using this additive property of view factors. So I don't want to say much more about this. I'm sure this will not be very clear now. When you see the example, you will be able to see, or you will be able to, I think, better appreciate what how these view factors can be much more helpful than maybe perceivable, I think, as a first in the first introduction that I'm giving here. Okay, so that is all about view factors. So now remember that view factors will be an integral quantity that we will use throughout radiation calculations, and they will actually help us a lot going forward when we do much more complicated, or consider much more complicated scenarios, as you will see shortly. If not today, maybe by the next lecture. So let's now begin with formal radiation exchange analysis. And I will start with black body radiation exchange, which is the easiest example before I move on to the more general case. And by black body radiation exchange, I mean we have two surfaces which are black. Let's say surface I, which is at temperature Ti, and maybe some surface J, which is at temperature Tj, Both have their own normal vectors, although they would not be important here, as you will see. Okay, so I want to, let's say, calculate for these two black bodies what is the net radiation exchange between these two surfaces. Remember, these are black bodies, and we are saying how much would be the net exchange between these two surfaces. Now, because I'm saying these are black bodies, what it means is if I plot the radiation on the surface of, let's say, this black body, so what we will expect, or what we can expect, is that the radiation intensity would be the same. It's a black body, so the radiation intensity will be the same. It would be, it's a diffuse emitter. So the surface will actually be will be a diffuse emitter. More importantly, because it's a black body, so it will absorb all incident radiation, which means that Ji, which is the intensity or the radiosity leaving surface I, should be equal to the total hemispherical emissive power from the surface, EBI. So B, anyway, remember B denotes, subscript B denotes emission from a black body. So EBI will actually be the total radiation given out by this black body. And that's because, as I said, this surface is a black body, so it can emit only as, I mean, it can only emit, or it will emit in the maximum way or in the maximum amount, and whatever radiation is incident, it will actually absorb. It will not be able, it will not reflect. And that is the reason why we are looking at black body radiation exchange in the first place, because there is no reflection from surfaces, which actually complicates the problem a little bit. So now we need to calculate how much radiation, or what is the net radiation exchange. So what I need to do is calculate q I to j, and then calculate q j to I, and the difference of them will actually give me what is the net radiation exchange between these two surfaces. So q I to j will just be ai Fij times Ji, which is the definition of net radiation exchange, or rather the radiation leaving surface I and being intercepted by surface J. And now remember that Ji in this case is just EBI. So we'll have Ai Fij. EBI is the radiation leaving surface I and being intercepted by surface J. Similarly, Qj to I will be Aj Fji into Ebj. So clearly Qij, which I'm going to call as the net rate of emission. Now I'm dropping the arrows. So this, let's say, is Qij minus Qji. So this will be Ai Fij Ebi minus Aj Fji Ebj. And now if I use reciprocity, that Ai Fij is the same as Aj Fji, I can write this as Ai Fij, take out as a common factor. Ebi and Ebj can be written as sigma Ti to the power 4 minus Tj to the power 4. So this is Qij. So radiation exchange between two black bodies can be written in terms of now the temperatures. So we are getting to the Stephen, or the form of the Stephen Boltzmann law that you guys are familiar with, especially when you have used this probably in the 12th standard, or maybe in JE. But now we are going there, almost getting there. So we can see that this form of, these functions are actually going to start appearing now. Sigma t to the power 4 with the difference of two functions. Now this was surface I to j. If I had an enclosure with n surfaces, it is easy to see that the total radiation or total intensity of total amount of radiant energy exchanged by surface I in an N enclosure or in an N surface enclosure would just be summation of J going from 1 to N of AI Fij sigma Ti 4 minus Tj4. So if you had any N black bodies in the enclosure, then clearly this is for 2. So if I add more, then this would be the total or net radiation exchanged by surface I with those other surfaces. But of course, it requires that all surfaces should be black bodies. So it has its meaning, it has its utility, that as a first calculation, this could be the way you can start when you don't know anything about the surface properties, right? If you don't know what kind of emission the surface has, I mean, its emissivity is not known. This could be the starting point to do any estimation of what could be the net radiation exchange between bodies. But what is more realistic is if you look at real surfaces. So we will look at radiation exchange this time between real surfaces, except when I say real, for these purposes we will talk about diffuse and gray surfaces, which are in an enclosure. And what I mean by that is, in terms of a, if you can sketch it now. So let's say we have an enclosure again made of n surfaces, but this time the surfaces are not black, but we assume that they are diffuse and gray. So what is the net radiation exchange by each surface? So what it means is, if I look at again counting of surfaces, let's say this is surface 1 with temperature T1, area A1, its emissivity as epsilon 1, and so on and so forth, until let's say we are at some surface I, and then all the way to surface N, right? So dot dot dot. So we can label all those surfaces. So the question that is being asked is, what would be the radiation exchanged by surface I with the rest of the surfaces in this enclosure? Now the problem is slightly complicated, as I said, from the black body case, because in this situation, if a surface I has some, let's say, radiosity Gi, sorry, not radiosity, irradiation Gi, the all of irradiation is not absorbed by the surface, but some would actually even get reflected. So some of this intensity gets reflected, and so what you get from emerging from each surface is its radiosity, which has some form, some component of irradiation and some component of emission. And this reflection, so this emission or this irradiation that reaches surface I must have originated from some other surface. So this irradiation does not get completely absorbed, rather it would reflect many times inside the enclosure until it's completely absorbed. So you need to do complete accounting of radiation emerging from each and every surface. So that makes it slightly complicated, because this is not easy that way, that how many reflections does it count. If you start counting, then it will actually drive anybody crazy. So there's a simpler way of doing this, which is what I'm going to present. But to do this, we'll make a few assumptions. So what we'll assume is that each surface is isothermal. So in totality, its temperature remains the same, and it has uniform radiosity as we assumed for calculation of the view factor, and it also has uniform irradiation. So that is one. The second thing that I will assume is that the surfaces are opaque. Opaque would mean that they don't transmit any irradiation. They're diffuse, so direction dependence is gone, and they exhibit gray surface behavior. The third assumption that we make, as always, is that the medium is non-participating. So the enclosure, whatever is the surroundings in the enclosure, or whatever is the medium, that has no influence on radiation exchange. And for now, let's say the temperature associated with each surface is known. Temperature Ti for each surface is known. Temperature Ti for each surface is known. So what we want to now calculate is the net radiant energy exchange from each surface, or by each surface. So how much radiation is each surface exchanging with its neighborhood. So the way to do this is as follows. Let's say we look at surface I. Let's say this is surface I in the enclosure. So it is getting some irradiation Gi from the rest of the surfaces in the enclosure, and it is also going to give out some irradiation, some radiosity Ji. So to maintain its temperature, and if I draw a control volume around this surface I, to maintain its temperature, unless Gi and Ji are equal, I would have to either supply some energy or maybe remove some energy from this surface to maintain its temperature at Ti. So let me say I'm going to add Qi as the energy to maintain its temperature. So Qi would just be Ai, or difference of the radiosity and the irradiation. So Gi minus Gi. If you do a balance, how much is coming in and how much is going out. So Qi and GiAi are coming in, and JiAi is going out. So Qi should be equal to Ai into Ji minus Gi. That is just a basic balance. Now, radiosity, the way we define radiosity is, it is the emission from a surface plus any reflection of irradiation. So rho I being the reflection or reflectivity, and Gi being the irradiation, we can write Ji in that manner. Now, because the surface is opaque, rho I becomes 1 minus alpha I. There is no transmission of irradiation. So for opaque surfaces, alpha I plus rho I is 1. Further, if I, as I have assumed that the surfaces are gray, it is a gray and diffuse surface, it means that alpha I should actually be equal to epsilon I. So this becomes Ei plus 1 minus epsilon I Gi, because the surfaces are gray and diffuse. Please remember. So I can now write radiosity as Ei. Ei would be epsilon I times Ebi, which is basically emissivity times the total spectral power from a black body, plus 1 minus epsilon I gi. And so I can write gi in terms of ji and ebi. It would be ji minus epsilon I ebi by 1 minus epsilon I. So that is the irradiation on this surface. Now what I'm going to do is I'm going to plug this irradiation into this equation for qi, because my objective is to calculate qi. So let's plug it in there. So we'll get qi to be ai times ji minus ji minus epsilon I ebi by 1 minus epsilon I, and that becomes equal to ai. So ji minus ji epsilon I minus ji plus epsilon I ebi by 1 minus epsilon I. So this cancels, and I can pull out epsilon I. So we'll get this as ebi minus ji by 1 minus epsilon I divided by epsilon I ai. So I've just pulled out or pulled down epsilon and a in the denominator. So what this equation is telling me is that for diffuse gray surfaces in an enclosure, the rate of energy leaving or required to maintain or to be removed, it depends on, I'll discuss that very soon. Now the energy rate at which energy has to be provided, let's say, is given in terms of the difference between the black body radiation and the radiosity, with something in the denominator. Now this sort of should remind you of the electrical circuit analogy that we did during conduction problems. So what it's saying here is that we can represent this by a network element, that there is a potential of EBI and there is a potential of JI, and they're connected by a resistance whose value is 1 minus epsilon I by epsilon I AI. And Q becomes the current which is passing through this network. So EBI minus JI is sort of like the potential difference, and or you can say it's a driving potential for this heat to be transferred. And 1 minus epsilon I by epsilon I AI is what we will call as a surface radiative resistance. So don't go by the units that we used in conduction. In conduction, we had temperature as a potential, and the resistance was because of either the conductivity, or in convection we had it because of heat transfer coefficient. Here we have a different form of writing these potentials and the resistances, but the idea is the same, that there's a heat current which has to flow, and it has to flow through this certain resistance between two potentials. Now what it means is, if EBI is more than JI, what is EBI? By the way, EBI is a maximum emission from this body which is at a temperature Ti. So if the body was to behave like a black body, if the surface was to behave like a black body, it would be emitting at the rate of EBI. So if EBI was more than JI, and remember EBI is only dependent on temperature, it does not depend on anything else. It only depends on the surface temperature. So if EBI is more than JI, it means that you will have net radiation which is being transferred from the surface. So the surface is basically transferring radiation, and so you will have to provide external heat externally to be able to maintain the temperature of the surface at Ti. Okay, so Qi will basically go from left to right in the network, and you will have to keep providing Qi to be able to maintain that temperature Ti. Conversely, if EB was less than Ji, then you have to keep removing, or there is net radiation transfer to the surface. So there's net radiation transfer to the surface, in which case you will have to keep removing this heat, or this rate of energy coming into the to the surface to maintain its temperature at Ti. So there are two cases. One is heat has to be, or energy has to be provided externally. The other case is energy has to be removed from the surface to be able to maintain its temperature. Okay. Now there's a catch here, which I have not mentioned so far. Even though I mentioned that the Ti is known, the surface temperatures are known, I didn't say anything about Ji. And let me now complete the picture in saying that Ji is an unknown as of now. We don't know what Ji is. I have not told you about it, but I said if Ji was known, then this is what is going to be is going to happen. Either heat will have to be supplied, or heat will have to be removed. So let's talk about Ji now. How do we get Ji? So if I go back to the enclosure, if I go back to this enclosure again, I know that the irradiation on a surface I should be a result of radiosities starting or emanating from all other surfaces, including itself. I mean, if the surface itself was concave, it can actually be seen by itself. So Gi, and please listen to this carefully. I don't know how many of you will be able to grasp it now, but think about this. Gi that I see here should be a contribution of J's from each and every surface. So that is what is Gi. Gi is basically the irradiation. It must be coming from somewhere. So that irradiation is coming from as radiosities from other surfaces. So I can write from an energy balance, if you can say it, that the total irradiation or energy because of irradiation received on the surface I to be the same as Fji Aj Jj. And there are too many J's now in this. I just realized. So Jj is the radiosity of surface J. Multiply that by Aj, that becomes the radiant energy that's leaving surface J. Fji would mean the view factor. So how much of radiant energy leaving surface J is being intercepted by surface I, and that is what is radiosity. Okay, it's intercepted. It doesn't mean how much is being captured, absorbed, or reflected. That's not the point. How much is reaching surface I is radiosity, or is irradiation. So that is a basic balance. And now if I use this, I can use the view factor to write this equation as, or rather, I can use the reciprocity relation to write this as AI Fij Jj. So AJFJI is AI Fij, which means I can cancel this AI because that is not independent. That's not dependent on the summation rule. So GI could be written as J12N Fij Jj, and so now I will plug this into the definition of Qi. So Qi was AI Ji minus Gi, which I can write as AI Ji minus summation Fij Jj. Now I also notice that there's a coefficient of 1 here in front of Ji. So I can replace that 1 with summation Fij. because summation Fij is 1. So I can write this as Ai summation Fij from j going to 1 to n times ji minus summation Fij j going from 1 to n jj, and that becomes Ai, and I can pull Ai inside just to show you what I'm going to write eventually. I can write this as summation j going from 1 to n Ai Fij ji minus jj. So what it's saying is that the rate of radiant energy leaving or required to be to maintain, or rather the rate at which energy has to be supplied to surface I, should be this difference of ji minus jj, or this difference ji minus jj with some uh, factor in the front. So this factor is what we call as a geometrical resistance, or inverse of geometrical resistance, I should say, because this is inverse of geometrical resistance, because the resistance will be 1 by Ai Fij. And more importantly, it basically is saying that the rate at which energy is to be supplied to I has to be the same as the rate at which energy from surface I is going to surface, individually surface j's. So it is sum of energy going through each and every, to each and every surface j. That is that I'm writing as qij. So this, the last thing that I'm going to do now is just to show you how this works out now in the network that we had drawn. So remember we had EBI with QI coming in, and there was a resistance that took us to JI. The resistance was 1 minus epsilon I by epsilon I AI. Now what I'm saying is beyond this JI, there are additional set of resistances. So the additional resistances are between potentials of Ji and Jj, or rather, let me put J1 first. Between other surfaces, so J2, J3, maybe till Jn, where we have this dot 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 where all the surfaces are there. Individually, each one is offering a resistance of Ai, let's say Fi1 inverse. This will be Ai Fi2 inverse, Ai Fi3 inverse, and this will be Ai Fin inverse, and Qi coming in at this point to this node, because see, remember Qi is coming here, so it is the current which reaches this radiosity Jj. So that gets split into, as by what I've written here, it gets split into various radiosities. So it gets split into Qi1, maybe Qi2, Qi3, and finally let's say Qin. And so when we do our calculations, we will actually be using this concept that radiation, or when we do this calculation in an enclosure, we will have this contribution, or we will know that current coming into a node which is Ji. Okay, the current coming into the radiosity node Ji will be split into n number of currents, each one of them flowing through its own resistance, and the resistance is going to be governed by the view factor. Okay, so this will be the final network representation that we will use in our radiation analysis. And this is actually quite a powerful tool to do these kinds of calculations. Okay, so thank you.